Robot R1 Reinforcement Learning for Enhanced Embodied Reasoning in Robotics. So, we are going to take a look into this paper. Large vision language models have recently shown great promise in advancing robotics by combining embodied reasoning with robot control. A common approach involves training on embodied reasoning tasks related to robot control using supervised fine-tuning (SFT). However, SFT datasets are often heuristically constructed and not explicitly optimized for improving robot controls. Okay, so we are going to take a look into this. Let's see the figure real quick. So, collect robot state from expert demo, robot state XYZ to robot state expert Y bar Z bar. Create various MCQ question answering. So robots, next state, current state, move right and down, question and answers. Train the model, question, correct or wrong. Large visual language model, think the button is, and reward, GRPO. So this is the reinforcement learning feedback loop. Okay, so this is the illustration of the robot R1 framework, and the method, we will take a look into those. The reward, GRPO objective function, illustration of the robot R1 benchmark datasets, and results here. So interesting, 0.96 for movement performance on embedded reasoning tasks tailored for low level control evaluated using the robot R1 benchmark. Robot R1 achieves the highest overall performance, outperforming leading commercial models across benchmark scores. Okay. 0.96 for movement in, 0.56 movement out, both are the highest. Load 3.5 comes same, and movement in, GPT-40 mini. Alright, average is highest, 0.76, and special in, out, average, all are highest. Gemini 2.0 flash comes close, 4 in, so and so. Tailored result for high level control, planning and subtask. GPT-4 does better in planning, 1.96, and subtasks also 2.02. Okay, but it still significantly outperforms SFT, the benchmark baseline training method. So let's look at the MCQA system. For instance, current visual input, you will receive a single combined image for scene understanding, front view of the workspace. The world coordinate frame follow these conventions. X-axis front of table positive to back of table negative, y-axis left negative, right positive, z-axis down toward floor negative, up towards ceiling positive. So standard stuff. Wrist view has the y-axis left and right opposite. World origin 0.25. Then we have 0.250, 0.752, so that is at the center of the table surface. Robot specification, gripper dimensions, 0.06 width, x direction plus 0.2 length, y direction. So y direction is longer, times 0.09 height. Sorry. Yeah. So in that direction, height. So y direction is the longest with fingers 0.04 in length. And current robot state XYZ, choice question. Based on the provided image and current robot state, predict the next waypoint position XYZ. Choose the most accurate option A, B, C, D. You first think about the reasoning process as an internal monologue and then provide the final answer. The reasoning process must be enclosed within think text, and answer must be within answer text. Alright. Alright. Then we have primitive movement prediction. What movements are needed to go to the next point to perform the task? Then we have waypoint prediction. Let's determine the next robot state to execute this task. Uh, planning. So move the gripper to align vertically and position just above the red button. Move the gripper down for pressing the button. So this is like planning, where GPT-4 is still performing better. Subtask. Move the gripper to align vertically and position just above the red button. Move front, slightly move right, and move down. Then we have current state prediction. Let us predict the current robot state based on an input image. So it is visual input for scene understanding. So here is an example question. What is the complete sequence of high-level actions needed to turn on the lamp? So here is the robot arm and the lamp as shown in the image. So model row answer. First it thinks. So determine the sequence of first typical steps required and blah blah blah. Answer: move the robot arm toward the lamp to interact with the lamp to turn it on. So this is the model answer, and then this is the ground truth answer. LLM is judge result also here, score. So this paper is advocating for LLVMs for robot control over supervised fine tunings. So large vision language models is shown to be better than supervised fine tuning based methods. And it is using the once again group relative policy optimization for the reinforcement learning. So generating multiple responses for a given query and then evaluates this response using a Riyadh model. Also applies KL penalty to ensure stability. Let's take a look at the new benchmark that has been introduced in this paper, Robot R1. Robot R1. So open-ended question answer tasks. So the purpose is designed to evaluate the nuanced reasoning processes behind robotic behavior, focusing on how well model can reason about robot actions based on visual inputs and task instructions. So open-ended QA format. Unlike traditional MCQA, Robot R1 branch adopts an open-ended QA format. Visually grounded scenarios and fine-grained evaluation, high-level action planning, subtask reasoning, primitive movement reasoning, spatial reasoning, A dataset consists of 10 tasks from RL branch with 5 frames randomly sampled from expert demonstrations for each task. We are talking about sampling from images here, resulting in a total of 50 images. So 5 times 10. So for each image, experienced researchers manually created questions and detailed reference answers targeting the 4 key reasoning abilities. And the final dataset includes 215 open-ended questions, 65 for spatial reasoning and 50 for each of the other 3 reasoning types. And we have already seen the evaluation, model responses, and LLM as judge. Rubric based scoring, and the result shows that it's trained with robot R1 achieves significant performance improvements across both low level and high level reasoning. It is also sensitive to model quality, with performance improving consistently with model version updates. Key conclusions. So effectiveness of reinforcement learning, of course, using GRPO. Uh, Improve performance on embodied reasoning tasks. So action control, low level action control in spatial, such as spatial and primitive movement reasoning. Generalization and transferability. So capabilities learned through robot R1 are shown to be to transfer effectively to other tasks. And it is sensitive to model quality. It provides a realistic and comprehensive evaluation of embodied reasoning capabilities. It reflects practical use cases by employing an open-ended QA format and visually grounded scenarios. So the limitations, for instance, focus only on the current XYZ position without considering the rotation of the end effector and the gripper movement. Feature could integrate these additional state dimensions. Potential risk of unintended actions by robots trained through reinforcement learning. Alright.